Okay, this is Dr. James, and today we're going to use a tiny network analyzer here, some coils and capacitor type electrodes, to measure plasma instabilities with a neon light bulb. See that? A neon light bulb. So it's lit up with 110, 60 hertz oscillating AC signal, and that'll make it easier for us to detect if there's some RF going or interaction with the network analyzer signal or not. Okay, so the idea is that this network analyzer here, let me turn this light bulb off so don't get shocked by it. Okay, so the network analyzer is able to send out an RF wave of different frequencies. It sweeps through the frequencies, and it comes out of this little cable here at the bottom, and it will go down to our either a capacitor or inductor. There's some inductors here too. Some inductors and made a little capacitor here out of pennies. And it'll send an RF signal which will interact with the plasma. The plasma has dielectric properties. It has actually negative, has instabilities, so it has negative, because of negative resistance, it can act like an amplifier. It can shift the phase or absorb or even amplify signals at certain frequencies. And that wave will, once it goes from the network analyzer here down to our electrodes or coils or whatever here to our light bulb, the light bulb will interact with the wave, create plasma instabilities or change the dielectric constant or the absorption, and send back a different wave, which can be measured here at the network analyzer. We can see that the plasma actually interacts with the waves that we sent down. Very cool. We're going to create plasma instabilities with a network analyzer. And network analyzer will sweep through the frequencies. Different materials will have like a fingerprint, depending on different shaped spectrum, different responses at different frequencies depending on the material. And plasmas are no exception. They'll have their own response. Very cool. Let's get started. Okay, so here's an experiment where I just wanted to see if I can excite plasma waves using a coil and a neon light bulb. Got the neon here. Let's take a look in here. There's a neon light bulb right there, and I can turn the power on and off to it. Okay, let's put the coil around that guy. Okay. And here is our network analyzer, and I was just looking over the range to see where it would respond, and it's in the range of 150 to 200 megahertz. Okay, so let's try flipping the power on and off. Right now the power is off. Put this out of there. Okay, we'll flip the power on. You can see that there's ripples generated. It is a 60 hertz signal going to the light bulb. You see the light bulb is on. Okay. And so in this range we are generating a plasma that is affecting the phase. The purple trace is the phase. We're looking at S11, the reflection basically. Basically this is a network analyzer. It sends a wave out to the coil and then it sees how the load responds. The load is the plasma. And then it looks at the reflected wave. And this yellow trace is the amplitude of that wave returning, or what we call the reflection, and the pink one is the phase. So when it's on, we are generating some kind of interaction. We're generating a wave, and that's absorbing or changing the phase of the power. And then when I turn it off, it goes away. So it looks like we're definitely able to measure plasma waves using our network analyzer. Very cool, huh? Okay. And this is in the range of, let's see, let me get my cursor over there. See where these resonances might be due to the coil. Okay. So that first cursor is at, oh, where's the frequency of my cursor? Okay. 190 megahertz up there. And this resonance here is 170 I'll try a different coil and see if the shape changes, because the coil is going to affect the response also. We can definitely see interaction. Okay, I turned off the light and see that goes away. Okay, so we'll try a different size coil. This is about that big. I have some smaller coils, maybe I'll try them. Okay, so here I'm looking over 200 to 300 megahertz range, and I put it on scale of 1 division per 1 dB per division at the top. Okay, and the light bulb is off right now. We'll try turning the light bulb on. The neon light. Look at that. We are definitely getting plasma interacting with our RF spectrum, or our RF signal generator, spectrum network analyzer. Look at that. Pretty big response. 200 to 300 megahertz range. Wow. Okay. And of course, those ripples are due to the fact that we have a 60 hertz signal going on there, and this is sampling at kind of a slow rate. So sometimes the light bulb's on, sometimes it's off, so it's producing a good wiggly line, so we can see that there's actually a signal there rather than a DC offset. Okay. I turn the light bulb off, and that goes away. 200 and 300 megahertz. Very cool. Okay, so I just wanted to look at the very low frequencies. The lowest this network analyzer goes down to is 50 kilohertz. And so it's going to look over 50 kilohertz to 1 megahertz, because this range here, about 1 megahertz range, seems to be something that you can be able to see. Oh, actually, I wanted to go to 100 megahertz. Let's see. We'll go to stimulus, stop, 100 megahertz. Okay, there we go. And it looks like I have it on too big of a dB scale. The scale is too small, actually. We'll change the scale to 1x. Okay. Let's see if we see some frequencies down here. Okay. So light bulb is off. Turn it on. Okay, it's definitely on in there. Maybe there's some ripples, but they're not as big down here. Yeah, there's definitely some plasma instability right in this region here. Okay. We can see the phase shifting a little bit there too, the purple trace. Okay, see the peak shifting. Okay, very cool. I'll turn that off. Okay, so I was going to look at the high end here, 900 megahertz to a gigahertz, and light bulb is off right now. Okay, let's try turning her on and see if we see any ripples. Okay, not really seeing too much. So up here we're not really getting. It's probably a pretty big mismatch though. This coil probably looks like a big mismatch at 3 or 1 gigahertz. And so it's probably not a lot of RF is getting into the actual coil. I'll try some lower frequencies. Okay, so here I changed the range from 600 to 700 megahertz, and let's see if we see any response there. The light bulb is off. I'll turn it on. I think I'm seeing some ripples there. Okay. Okay, it's off. Yeah, see it smooths up. Turn it on. We're definitely getting some ripples there due to the plasma changing the interaction inside the coil. I guess would be the magnetic susceptibility. Okay. Maybe I'll try doing some experiments with treating this as a dielectric too, rather than looking at the the magnetic portion of this plasma, we could look at the electric portion. But yeah, it definitely looks like we are getting ripples due to the plasma being turned on and off at 60 Hertz. Very cool, huh? With the smaller coil now, and I just made a capacitor out of 2 pennies, and I kind of taped them together. And hopefully I don't short out the 110 there. Okay, and this is what I did with the other one. I looked over a big range to see where I saw some interesting things happening, and then I zoomed into the smaller range. Let me try turning our light bulb on. There we go, we got the light bulb on. And actually I wasn't watching this. Let's see if I just jumped or not. Yeah, it's hard to tell. I'm going to have to zoom in on a smaller range. Okay. Okay, so here we go. We got the light bulb off, and I'm looking over the range 600 to 700 megahertz. And let me turn the plasma on. Look at that. Lots of ripples up there, so it definitely has a response to the RF at these high frequencies here. Very cool, huh? Okay, light bulb's off. See, on. You can see the ripples. Off. No ripples. Very cool. Capacitor actually has a flatter response in the coil, so I can. Part of the problem was before with the coils, I think, is they had all big dips and stuff, so it's hard to zoom in on the response when you have those big dips like that. But this is 700 to 800 megahertz, and we'll see if the plasma responds to these frequencies, and it certainly does pretty well. Look at that. Okay, light bulb is on, off. On, off. So definitely responding to those frequencies. Those are pretty high frequencies too. Okay, we'll try a little bit higher frequency, 800 to 900 megahertz. And the light bulb is off right now. Got the light bulb off. So let's try turning the light bulb on. I think I see some ripples there, but I think they're smaller now. Definitely see the light bulb is on there. Okay. So I think the response is starting to die down at these frequencies. Okay, and here is 900 to 1 gig, or 1000. And we have our light bulb off. We'll turn her on. And I might see some ripples there still. They're getting very small though. Okay, I'll turn it off so we can see the difference. Yeah, maybe not. Yeah, that might be just noise at that frequency up there. Yeah, I know this is on right now, so I don't see any difference. So I guess we don't get too much of a response up to almost a gigahertz, but up to about 800 megahertz, 900 megahertz, less than 900 megahertz, we are getting plasma oscillations due to our excitations from our network analyzer here. Okay, very cool. Anyway, some very cool plasma physics experiments that you can do with your own in your own home. Be careful. I put about I think an 80K resistor. I think the internet suggests anything between 10K and 200K. If you don't get a neon light bulb with a resistor, you need to put a resistor in there, or it will blow up. It will run too much current through there, and it looks. You don't want to be around when that happens. It will vaporize something probably. Hopefully not catch something on fire. So anyway, very cool. I'll if you're interested in doing these type of experiments, I will post links in the back. Have my Amazon links also. If you click on those, it will help me out, help this channel out. Won't cost you anything. I'll put links to the tiny network analyzer that I used and these neon light bulbs, and I think that's probably about it. Anyway, very cool experiment. This is Dr. Janes, and thanks for watching.